Stanford University.
All right, we were talking about something called T-duality. T-duality was very, very important to the history of the mathematical developments of string theory. Let's go back over it again and discuss it a little more fully. And then I want to tell you how it led to the concept of D-branes and how D-branes have become something of a mathematical tool for studying quantum field theories, the kind of quantum field theories that have nothing to do with gravity, but the kind of quantum field theories that we use on a day-to-day basis to understand hadrons, quantum electrodynamics, and even quantum field theories that are interesting to condensed matter physicists. We won't get to all of this. Obviously, we won't get to this today. But I'll just try to give you some a picture of what it's about. All right, we imagined that there were some compact directions of, compact means these small ones which were rolled up. For simplicity, I will imagine that the compactification is toroidal, on tori. In other words, not necessarily two-dimensional torus. A one-dimensional torus is a circle or a line interval with the endpoints being identified. A two-dimensional torus is a a parallelogram. Doesn't have to be straight. A parallelogram with opposite sides identified. A three-dimensional torus is a cube, or not necessarily a cube, but a parallelepiped, thank you. A parallelepiped with opposite faces identified, this point and that point, this point and that point, and in the front and the back. So in general, in any dimension, the concept of a torus is a well-defined concept. And those are the easiest cases to study. Those are the easiest cases to study. In these cases, of course, supplemented on top of this is the ordinary 4 dimensions of space-time. So this is what's present at every point of space-time, ordinary space-time. There are other directions that we can move in, or that somebody small enough can move in. And that's the setup. Now, let's focus on one particular place in space-time and ask what could be there. A particle can be there. But now let's zero in and zoom in and ask what that particle looks like on scales which are so small that these compact directions become visible. So let's start with a simple picture that we had just to get started. We imagined one large direction and one small direction. The small direction now would be called a circle. A circle not because it's embedded in 2 dimensions and looks like a circle, but just because its head eats its tail. That when you go around, you come back to the same place. All right, so that's our space-time. Where's time? Oh, I don't know. Time is, add time into it. Time is not drawn on the blackboard. This is pure space. Okay. In this case, 2-dimensional. But if you like, we can generalize it to higher dimensions. The compact directions become tori. The non-compact directions, the big ones, just become our 3 dimensions of space, or however many dimensions of space we want. Now, in string theory, particles are strings. Let's take the case of, not all string theories are the same. They're different from each other, but there's a fairly small classification of them. The string theories that I'm interested in right now have only closed strings. We're going to come back to what happens when you have open strings in a little while. But for the moment, only closed strings. No endpoints. That's number one. So they're like rubber bands. They're like rubber bands. Here they are, closed. And furthermore, they're what we call oriented. Oriented means that there's an intrinsic difference between going around the string in one direction rather than in the other direction. It's mathematically like a rubber band in which on the rubber band we drew a series of arrows to indicate direction around. And we'll keep track of that orientation. An example of what that orientation would say is when the string splits, when it splits like this, it will split into two strings with the same orientation on the blackboard. So in that sense, orientation is preserved for these strings. They remember a sense of which. Now, of course, that doesn't mean that they're inequivalent. I mean, there may be a symmetry in the sense that a string with the opposite orientation may have all the same properties, but what it does mean is that you can compare two strings to see whether they have the same orientation or the opposite orientation. Same with electric charge. Positive electric charges behave exactly the same way as negative electric charges in that, for example, if you replaced in the real world every electron by a positron, every proton by an antiproton, and with it every neutron by an antineutron, chemistry would remain exactly the same, or at least to a very, very high precision would remain unchanged. So in that sense, plus charges are identical to minus charges, but you can tell the difference between a plus, you can't tell the difference between a plus charge and a minus charge, but if you have two charges, you can tell whether they are the same or opposite. How? Just see whether they attract or repel. You can't tell whether they're both plus or whether they're both minus, but you can tell. Okay, so the same is true of oriented strings, that they have a sense of orientation. If you replaced every string in string theory by a string of the opposite orientation, the theory would be the same, but if you have two strings, you can tell whether they're the same orientation or the opposite. Let's just call them oriented strings. Now you can wrap them, well, you can do two things. You can have a string which is not wound around some compact direction. There it is. It's just drawn on the surface of the two-dimensional world here. It's free to move. It can move in this direction or it can move around. So it can have momentum. And that momentum can be along the direction of the large directions, or it can be along the short directions. Or it can be a combination of both. It can, when I say it has momentum, we can think of that as motion. And it can move this way, it can move this way, or it can even move in a helical pattern like that, having both components of momentum. The components of the momentum in the short directions, in the finite compact directions, are quantized. They are quantized in integer multiples of the inverse radius, or the inverse circumference, the distance around the closed, it's called a cycle, around the closed cycle.
Do the strings have to go all the way around the cylinder, or can they be like you drew it there?
This one isn't going all the ways around. What do you?
Well, they didn't. I thought they went from like 0 to 2 pi. They closed. Oh, gosh.
In what space?
Sigma?
Ah, no. This is not sigma. This is some x. This could be x. We could call this direction y around here. That's space. That's real space. Sigma is just a parameter which changes along the string. It's just naming the points along the string. You have a rubber band, and the rubber band is composed of molecules. Okay? The molecules can be named. The first molecule is Harry, then George, then Fred, then Sarah, and so forth. That's sigma. It's naming the particles as you go around the string. Okay? And if the string is closed, then sigma comes back to itself.
Yeah, the size has to be the same along.
Is what?
Does the size of the compact direction have to be the same at every place in the long direction?
We'll come to that. The answer is no. No, it does not. But we'll come to that. Okay, so sigma varies along here, along the string, and it goes from 0 to 2 pi. But that has nothing whatever to do with whether the string is wrapped around space. So yeah, think of, I'm sorry I didn't bring a rubber band. Think of a rubber band where on the surface of the rubber band we've marked off sigma equals 0, sigma equals a small number or twice the small number as we go around the rubber band. Here it is, rubber band, and we mark off points on the rubber band. That's sigma. That sigma has nothing to do with whether I wrap the rubber band around my wrist or not. It's always there, it's sigma, it goes around. Once, as the string goes, as we follow the string around its own shape, sigma goes from 0 to 2 pi. It's a completely separate question of whether the string is wrapped around the extra dimension, in the same sense that a rubber band could be wrapped around my wrist. You can wrap the rubber band around your wrist. If it's an oriented rubber band, you can wrap it so that the arrows point this way, or so that the arrows point this way. So we have two kinds of wrapped strings. Here's a wrapped or wound. The correct term is wound. Wound around a compact direction. Here is one of them. It comes around the other side, and it points that way. Okay, that's one. The other one goes in the opposite direction. Okay. Let's take two wound strings like this. Two wound strings like this, let me just draw it a little differently. Let's do it this way. This one goes. What can happen to two wound strings which are wound in opposite direction? Well, remember, the basic process of string theory is for strings to come together and join and split. Now the rule is that when they join and split, orientation is remembered. A string like this and a string like this can, let's put some more orientation arrows on it. Let's ask how they can join. They can join like that. I don't think I need words to describe it. I think the picture describes it well enough. The lines have to be, or the arrows have to be continuous. Okay. What you can't have is a string splitting somehow like that. Here the line can't be continuous. You run into a contradiction as these points come together. All right, so this is the kind of thing that can happen. The opposite, namely the time reversal of it, can also happen. Strings which are like this can come together and join, and so forth. All right, that's the basic phenomena of splitting and joining, and it's the thing which is governed by a coupling constant. So what can happen here? What can happen is clear. This can happen. Oh, I lost track of the orientation. Now it's not really wound anymore. As from the point of view of topology, you can unwind it into this. All we've done here is we've taken this, we've stretched it around, and then joined it on the far side to form the original wound pair. Well, we can undo that, and now it's unwound. It's just a single unwound string. All right, now, one way to think about it is to keep track of winding number. Winding number can be defined to be positive for windings which look this way. We'll call that winding number 1, And if it's wound the other way, we'll call it winding number minus. I won't try to give you a mathematical definition, but winding it on my wrist, if the arrows point this way, we'll call that positive winding. If they point the other way, we'll call it negative winding. If I have a single string which is wound like so, what's the winding number? The winding number is +1. If I have another one, forget this one for the moment, just throw it over on the side. We have another one which is wound this way, that has winding number -1. The two together, all together have winding number 0. This has winding number 0, it's not wound around at all. So what's preserved is winding number. All right. Let's take another case. Let's imagine now two strings which are wound the same way. There's two strings wound the same way. What can happen to them? They have winding number 2. The sum of the two of them have winding number 2. What can happen? Well, let's draw it over here again. These are going this way, and they come around here. They're both going the same way. You can't unwind this. You can do something. You can have a process of splitting and joining which does this, which interconnects them a new way. Can you see what I've drawn? We've crossed them. We've crossed them, but still, after they've crossed, the arrows are still continuous. There's no contradiction in the direction of the arrows. This also has winding number 2. It's one string with winding number 2. This is two strings, each one with winding number 1. Each one with winding number 1, but the sum total of the winding numbers is 2. All right, so here's again another example. Winding number is conserved. You can't change the winding number, although you can change the number of connected components. So if you had winding number of 100, you could have one string wound around 100 times. You could have two strings each wound the same way 50 times. You could have 100 strings each wound once, and they can all communicate in the sense that you can morph from one configuration to the other, but you can't change the winding number. So winding number is an absolutely conserved quantity in this kind of string theory. It never can change. Let's forget we're going to come back to winding number in a moment. Well, maybe we should discuss winding number. Yeah, okay. This one over here, that can just be thought of as a tiny little particle. Let's just think of it as a little particle. It's a string, but it's a particle. What's it characterized by? It's characterized by components of momentum. It's characterized by many things, shape and all sorts of other things. But in particular, let's characterize it by its components of momentum. In particular, the component of momentum in this direction over here. The component of momentum in that direction has to be an integer number, let's call it n, integer number of a quantum of momentum, and the quantum of momentum has to do with the circumference. Let's just call it the radius around here, r. Distance around here I'll call r. It's a circumference strictly, but I'm just going to call it r, because r is the standard term for it. The quantum of momentum in this direction, and also incidentally, the quantum of energy in that direction, if these are massless particles, energy and momentum are proportional to each other. For example, if they were gravitons moving this way or this way, the energy is also quantized in that unit, and so the energy of the momentum the momentum can have either sign. It can be plus or minus. The momentum, the energy is always plus, for the same amount, n over r. It has momentum n over r, and it has an energy also n over r. Okay. That's the energy due to momentum, and in particular momentum along the small direction here. It's quantized. So that's unwound particles and the contribution of energy due to momentum. Oh, let's think about now what, what is the momentum of a string moving in space? Basically, it's just the velocity of the center of mass. It's just the velocity of the center, just like a rubber band, Its momentum is its mass density, which for simplicity we can take to be 1, times it's just its mass, which we can take to be 1 for a rubber band, times its velocity. So the velocity, the momentum is proportional to the velocity, and we can think of this as dx d tau. Tau is the time variable that describes the motion of the string in the simple quantum mechanics that we've described previously. And it's got to be in integer multiples. Now let's think about the wound strings, the strings which are wound around. What is the typical energy of a wound string? Well, strings have a certain tension. Let's just work in units in which that tension is 1, but tension is energy per unit length. Right? So for energy per unit length, if there's a given energy per unit length, then the energy of a wound string is not n divided by r, but it's some other integer. I'm going to call the other integer w. W stands for winding number, times r. The energy of a collection of strings which are wound around here are the integer winding number times r, whereas the energy of a string which is not wound around the compact direction is n divided by r. So I think we talked about this last time, but let's discuss it again a little bit. Let's suppose that r is very small. All right, here we have the spectrum of the strings which are not wound. The separation between the levels is large. Large because 1 over r is large. So it looks like this. With the separation being of order 1 over r. Here's n equals 0, here's n equals 1, and so forth. Now let's look at the spectrum of the wound strings. In other words, the energy levels of the wound strings. Those also come in integer multiples. Here's 0. Winding number 1, winding number 2, winding number -1, winding number -2. But now it's w times r. So that means if r is large, what did I say, r is large or r is small? I think I said r was small. What did I say? I said r is large or small? R is small. Okay, so that makes the separation large here, but it makes it very small here. Now let's go to the other extreme. I know that we talked about this before, but I want to reiterate it again. Let's go to the other extreme. This is r much less than some unit of length in string theory, the natural unit of length in string theory. Let's just call it 1. Here's r much bigger than 1. What do the energy levels look like? Well, for r much bigger than 1, 1 over r is small, and these excitations here are very close together. What about these? Here r is very large, so it takes a large energy to wrap around. And they look like this. Suppose all you knew, all you could measure about these particles, namely the things I'm talking about the things associated with the compact directions. The only thing that you can measure about the compact directions, let's suppose, was the energy of the particles. And you're trying to figure out what the radius of compactification, that's known as the radius of compactification. What is the radius of compactification? Well, your problem is, how do you tell the difference between particles which have energy with respect to the compact direction because they have momentum or because they have winding number? You can't, obviously. Just from the energy levels, you can't tell. So, with this particular spectrum, there's an ambiguity. Are you in a theory with a small compactification in which large separations between different momenta, small separations between different winding number, or are you in a world with a very large radius of compactification and in which the role of winding number and momentum has been interchanged? You think, well, maybe you can do a lot of other kind of experiments, maybe you could scatter these particles together, see what comes off. One of the very, very remarkable mathematical facts about string theory is that the inability to tell which kind of world you're in is rigorously correct for everything that you can calculate about these strings. Collisions between them, that two different theories with very different radii of compactification, if you interchange winding with let's call it with momentum around the compact direction, the theories behave in exactly the same way. So, conclusion, in certain sense, it doesn't make sense to think of the compactification as smaller than a certain size. There's a certain size where they cross over and where they interchange, and if the size of the compactification is smaller than that, it's just entirely equivalent to a larger compactification with winding and momentum interchange.
Quick question. Does that mean that the winding number is a mathematical convenience rather than a physical property?
I don't know what to say. It says that there's a symmetry. It says there's a symmetry, and that there's physicists use the term duality, which means an equivalence between different descriptions of the same thing.
Is there an R of interest where these two things are the same?
Mm-hmm. No. In some units, it's R equals 1, and there you have some extra special symmetry that not only can't you tell which kind of theory you're in, but you can't tell which are which. They're the same. Yes. There is a special point. Now, I wrote an equation over here that momentum is equal to dx d tau. Let me make that a little more precise. Every point on the string has a motion. In particular, I'm thinking about the motion around the compact direction, but different parts of the string could in principle be moving different than other parts of the string. It could be differentially moving in different directions, different speeds and so forth. The full momentum that we're talking about when we talk about the momentum is actually the sum of the momenta of all the little bits of string. You can either sum it, or you can think of it as an integral over the entire string of the velocity, the x d tau. And which x am I talking about? I'm talking about y, actually, the one that goes around the string, the y d tau. What about the winding number? Anybody got a mathematical expression for the winding number? Imagine now a string which is wound, the simplest possibility. It's wound around here. This is the y coordinate. The y-coordinate is periodic, it comes back to itself, but the string also has a sigma coordinate. The string also has a sigma coordinate, and that's embedded in the string. If the string is wound in this very simple way, another way of saying it is that sigma is proportional to y. Actually, y divided by the total radius of compactification, I guess. If y comes back to itself after going distance r, and sigma comes back to itself after going around once, then the right relationship is that sigma is y over r. It's just another way of saying that as you go around sigma, as you go around the rubber band goes around the y direction. Well, now look at this. Let's look at d sigma by dy. That's just 1 over r. d sigma by dy, let's just take d sigma by dy. d sigma by dy is proportional to the little spacing between here and here, and the total winding number is the sum of a little bit of d sigma dy as you go around the string. In other words, the winding number yeah, actually this is right. R times this, and the winding number, I believe, is what did I had an equation. Where did it go? Y over R is equal to sigma. So d sigma by dy is 1 over R. Is 1 over R. The total winding number is 1 over R times the integral dy by d sigma. dy by d sigma. Does this make sense that the total winding number, what's the integral of a derivative?
Why? What you started out?
Usually the integral of a derivative in lots of cases is just plain 0. If a thing comes back to itself when you go all the ways around. But y doesn't come back to itself when you go all the ways around. Y itself changes by 2 pi. So the integral dy d sigma is just the total number of times that the string wraps around that direction. So this is kind of curious. T-duality, this funny duality between winding number and momentum, is equivalent to interchanging n and w, interchanging r and 1 over r, and interchanging dy d tau with dy d sigma. Funny mathematical construction. Keep that in mind, that T-duality is interchanging winding and momentum, interchanging r with 1 over r, and interchanging the derivative of y, that's the position of the string, dy d tau with dy by d sigma, where, dy by d tau with dy by d sigma. The derivative, this is partial derivative. It's pretty abstract, but this is an exact symmetry of string theory. If you make these interchanges, nothing changes.
And say it once again. If the symmetry is swap dy d tau.
Swap dy d tau for dy by d sigma. Now, the reason I introduced this, we'll see why. I didn't have to tell you this, but I'm telling you now because we're going to use it later.
Wouldn't that imply a relationship between tau and sigma?
No, there's no relationship. It's just you interchange them. Wherever you saw the expression dy by d tau, you replace it by the expression by dy by d sigma. It's a weird thing to do, But in all observable quantities, scattering amplitudes, energy levels, all of the properties of the string theory don't change if you make those changes. Let's talk about something else. Yeah.
Why would the string want to be wound around the dimension anyway?
They don't want anything.
So why would it ever get in that state? If it can be
Well,
in the other state while we're in this.
somebody may hit this string over here with some energy. Hitting it with some energy, among other things, may stretch it out. In fact, it may stretch out to look like this. You blast it with a lot of energy. I've drawn a very neat configuration over here, of course. But if I blasted it with a lot of energy, it might be much more complicated than that, but still have this kind of configuration. Now, once you've done that, and you take into account that strings split and join, then this can separate itself into two strings with opposite winding number. Once you've created two strings with opposite winding number that are no longer connected, they can separate from each other. They can separate from each other. And when they separate from each other, well, then you've got an isolated string with winding number 1 and another one that you can just send off to Alpha Centauri and never see it again. The answer is that in general, you cannot prevent it from happening. You may have to, in particular, if the distance around here is large, then it takes a large amount of energy to create these winding strings. Here it is. Well, let's see, the energy itself was proportional to R for a winding number. So with a small amount of energy, it's not going to happen. You don't have enough energy to stretch the string that far. But if you collide two strings with a large amount of energy, they splatter all over the place, they stretch out in wild and chaotic directions, and there's some probability that, that they'll reconnect. It will not change the total winding number, but it will take a single string, or perhaps two strings which are not wound, which collide with each other, and convert out of them something with two strings of opposite winding number. Once that happens, they can separate and they go off. So the answer is generally that it will happen in collisions if you don't have it that way to begin with. The same question occurs for electric charges. If you start with a neutral world, why are there electrons? Well, even if there weren't electrons, well, there's got to be something to start with. If there's nothing, there's nothing. But maybe you just started with photons. You take some photons, you collide them together, and what comes out is electrons and positrons. If you take the positrons and you throw them away, you don't throw them away, but you push them off to some distant place, you're left with electrons. That's all. So you can't forbid these things. You can't forbid them, and eventually you will create them. Now, these winding numbers and these momenta, these momentum quantum numbers, these quantized momentum, are not only in some sense similar to electric charge, but they have all of the properties of electric charge. In particular, two strings of opposite momentum, one going around one, can I do this? Let's see. Oh yeah, I can do it. Two strings going around the opposite way with respect to the big dimensions of space. So here they are. Two strings, these have the same, no, these have the same winding number. Okay, that's easy, that's this. Two strings with the same winding number will repel. I'll tell you why in a moment. Two strings with opposite winding number will attract. What is this attraction and repulsion? This attraction and repulsion actually corresponds to the gravitational attraction and repulsion of the higher dimensional theory. If we live in a world of, let's say, 3 dimensions, 3 space dimensions, and we add in one more tiny direction, then strings which are wound oppositely, maybe in different places in the big dimensions, different places in space. We have a string wrapped this way, we have a string wrapped that way. They'll attract each other if they have opposite winding number. They'll attract each other in our ordinary 3-dimensional sense. Likewise, if they have the same winding number, they will repel each other. So they behave like electrical charges. Where does electrical repulsion and attraction come from? It comes from the electromagnetic field. And of course, the electromagnetic field is deeply connected with photons and so forth. Where does this attraction come from? And the answer is it comes from gravitation. But not gravitation in the 4-dimensional sense, but gravitation in the 5-dimensional sense, in the extra-dimensional sense. In the theory with extra dimensions, the Einstein gravity in the extra dimensions manifests itself in the phenomenon of attraction between like momenta, cross it out, attraction between opposite momenta in the compact direction and repulsion of things with the same momenta. That's not obviously easy to see. I've told you this before. It's not something I'm telling you for the first time. And in fact, you can relate it to Einstein's field equations. I'm not going to relate it to Einstein field equations in any depth. I'm just going to discuss the origin of the electromagnetic field, or the analog electromagnetic field that's associated with this electrical type behavior of these particles. There must be something like an electric field, there must be something like a magnetic field if they're behaving so much like electrically charged particles. What is it? Okay, so first, just ordinary Maxwell equations. The electric and magnetic field are describable in terms of a vector potential, a 4-dimensional vector potential, A mu. You build up the magnetic field as the curl of the vector potential, and the electric field as related to the time derivative of the vector potential. It's a 4-vector. It has 4 components. Let's go to gravity in 5 dimensions. Gravity is described by a metric tensor. The metric tensor, let's call it GMN. Why don't I use mu and nu? Yeah. I'm saving mu and nu for the 4 dimensions of ordinary space-time, but we're now talking about a 5-dimensional world, so let's use for the 5-dimensional world M and N. But what do M and N run over? They run over the ordinary dimensions of ordinary space-time plus one more direction. So we can write GMN as having various components. G mu nu, that's the ordinary dimensions, and then G mu 5, 5 is the 5th extra dimension, and then what else? G 5, 5. Those are the components of the gravitational field. What about G5 mu? I wrote G mu 5, what about G5 mu? Symmetric tensors, yeah, the same thing. Okay, these are the independent components of the gravitational field in 5 dimensions. Well, this one here, that's just the metric of 4-dimensional space-time. So it's just the usual Einstein gravitational field, nothing new there. Here we have something that has an index. It has a 5 index here, but the 5 index is this hidden direction, we can't see it. But it also has a mu index, which means that it's a 4-vector. We would mistake this object for a 4-vector. It has 4 components. It's like a mu. Let's make that identification, because that is the correct identification. And what about G5, 5? that has no components in the usual four-dimensional sense, so it must be a scalar. That scalar is usually called phi, it's called a dilaton, or sometimes called a dilaton, but it's almost always called phi. What is G55? It's the component of the metric around the fifth direction. It tells you how big the fifth direction is. If G55 is big, it's just a metric. It's the square of the distance around the fifth direction is what it is. If G55 is big, the fifth direction is big. If G55 is small, the fifth direction is small. The metric tensor in 5 dimensions is a field. It can vary from place to place. All of these things can vary from place to place. This is just the usual gravitational field varying from place to place. This becomes an analog of the electromagnetic field, which can vary from place to place. And this is a scalar, which can vary from place to place. But what does that scalar mean? That scalar is the size of the fifth direction. That can vary from place to place. Somebody asked me that before, and you can imagine waves in space, where the waves of space are not waves of electromagnetism, they're not waves of gravity, they're waves of varying size for the fifth dimension. Okay, but nevertheless, the quiescent ordinary vacuum doesn't have such waves. It's fixed. Okay? But in general, the size can vary from place to place. Okay, this is an electromagnetic field. If this is an electromagnetic field, then it's also a gravitational field, and it's an analog electromagnetic field. Thought of as a gravitational field, what are the sources of gravitational field? There are things like energy and momentum. In particular, the sources of mixed components of the field like this are components of momentum. So the source of this component of the gravitational field is actually the momentum in the fifth direction, the flow of momentum in the fifth direction. That means that the source of this analog vector potential is going to be the component of momentum going around the fifth direction. Lesson: the momentum quantum number, the one, where is it? The momentum quantum number over here can be thought of as electric charge in an analog, what's on that? In the Kaluza-Klein theory, in which the mu5 component of the gravitational field is the electromagnetic field. Electric charge, momentum, electric field are component of the metric. Well, good. That's easy. That was easy. That was easy. What about, and of course, we go a little bit further, and we can say that that the electric field is associated with the graviton itself. Okay, now let's come to the winding number.
So I'm sorry, is phi then proportional to n, or?
No. N is an integer. It's related to r. It's related to r. It's not quantized. It's related to the size of that dimension. And it can vary from place to place continuously and smoothly. Right. It's called a dilaton. And it's a wave field that, if string theory was right, should exist in some form or another. But in any case, it's part of the mathematics of string theory. Let's come to the winding number now. I told you that the winding number also behaves with this property that opposite winding numbers attract, like winding numbers repel. They also behave like electric charges, but not the same kind of electric charge as the momentum quantum numbers. It's as if there were two kinds of electric fields, two kinds of electromagnetisms. living side by side, two kinds of photons, two kinds of charges, winding number associated with something we could call winding photons, and momentum quantum number associated with momentum photons, but momentum photons are just a piece of the gravitational field. In other words, they're gravitons which are polarized along the mu5 direction. So what are the field? What is the field or the analog of photons which is emitted and absorbed by winding number? Not by momentum, but by winding number. And here we know the answer. We'd have to go back several lectures to fairly early lectures. But let me remind you, this is probably something you've forgotten. I told you, but I don't think I stressed it very hard. Let's go back to the spectrum of closed strings. The closed strings, what kind of states are there of closed strings? Okay. We start with the closed string being totally unexcited, and then what do we do with it? We excite oscillations on it. We excite oscillations with the creation and annihilation operators which create and excite waves on the string. They're not creation and annihilation operators for particles, they're creation and annihilation operators for waves moving along the string. These are closed strings. Let me just remind you what kind of operators there are. There are creation and annihilation operators. I'll just think about creation operators. And I won't put a little plus because we'll wind up with too many indices. A creates a unit of excitation. What labels it? Well, first of all, the A's are labeled by directions of space perpendicular to the momentum of the object, of the string. So they're labeled by directions of space. Let's call it I. I can equal, if the string is going down the z-axis, it can be x, it can be y, no, it can be x1, x2, or it can be a compact direction y. So the i's vary over all the directions of space, including the ones which are wrapped up. That's one thing there. Now, what's the other index that depends on? The frequency of the oscillator. And that was an integer, and it tells you how much energy, when you create one of these oscillations, creates an energy proportional to n. All right, so n is related to the frequency. I is related to direction in space. And one more thing. You remember what it was? For closed strings. Whether the wave is propagating around the string. Remember, the string is oriented. There's little arrows. Whether the wave is going one way around the string or the other way around the string. I don't remember. Does anybody remember how we labeled the two? Let's just call it left-moving waves and right-moving waves. A-I-N. And left and right here are purely symbolic. They refer to the direction on the string, not left and right in real space. Okay, now there was a rule. I told you the rule. I called it level matching. It's a rule. I'm not going to go into the rule now. I think I explained it a little bit, what it had to do with, but it's a rule. And the rule is the amount of energy in left-moving waves must equal the amount of energy in right-moving waves. That's a fundamental rule of string theory. The mathematics goes to hell in a handbasket if you violate it. And so let's see what kind of states we have. We can first of all have the state with no energy in it at all. That's the tachyon. It's not there in superstring theory, but in the simple versions of the string theory. And it has -2 units of energy. We worked that out. -2 units of energy. And it's a tachyon. Bad thing. We don't want it. What's the first excitation? What's the next energy up? Well, the next energy up is to hit it with the lowest frequency oscillator, to excite 1 unit of energy with n equals 1. So, for example, we could hit it with AI. I can be any one of the directions of space. 1, the lowest oscillator, left, or A1I right, O. But neither of these states are a legitimate option. And the reason is because this one has 1 unit of left moving energy and no units of right moving energy. This one has 1 unit of right moving energy and no units of left moving energy. And so it doesn't satisfy this principle that the amount of energy in left and right have to balance. Okay, so these are gone. They're not there. What's the next thing up? The next thing up is to apply 2 units of the lowest oscillator, 1 left and 1 right, to make sure that you have balanced energy going in left and right. And that means AI1 left times AJ1 right. I and J are 2 directions of space. Okay, they are the 2 directions of space. For simplicity, let's imagine the directions of space are the usual 3 directions of space plus 1 more, namely the 5th direction, the thing that I called Y here. 1 more direction of space. The 1 more, and we apply this, of course, to the vacuum. These are the things we identified with graviton and other massless particles with polarizations that have to do with I and J. Well, there is something new when we add this 5th direction. 1 or both of these indices can now be in the 5th direction. Earlier, before we discussed the 5th direction, I and J could only be ordinary directions of space, and these corresponded to gravitons which have polarizations, they're like photons, they have polarizations, and the polarization is characterized by 2 directions of space. But now we have something new. We can have I be the ordinary direction of space, and this one being the 5th direction of space, the internal direction, the small direction. Okay, now we have something which has a vector index. The 5th direction here, we don't even call out a direction of space normally, and so it has the same kind of index structure that a photon would have. This is like a photon. It has a polarization, let's say moving down the z-axis. This could be polarized either x or y, or however many dimensions we have to worry about. And this is very similar to a photon now. Okay. But there are 2 ways to do it. You could have this one being left and this one being right, or you can have AI1 right, A15 left O. There are 2 possibilities now, and it seems like that means that there are 2 kinds of particles that behave like photons, that are similar to photons. The correct thing to do is to add them and subtract them in the sense of quantum mechanics to linear superpositions, but whatever there is, there's going to be 2 types of objects which have the index structure of a photon. There's going to be 2 kinds of photon fields. The one with the sum, that's identified with ordinary graviton moving down the z-axis. The other one is identified with another field, a separate field, that also has a structure similar to a photon, and guess what it is connected with? It is the field, the electromagnetic-like field, whose sources are what? Winding number. So 1 linear combination is associated with momentum, and 1 linear combination is associated with winding number. These 2 things, one of them is associated with gravitons, which are the field quanta of the gravitational field, and the other one is associated with something called B mu nu, which is different than the graviton, different properties, but also gives rise, its mixed component is also like a photon. So here's what we can say now. What is T-duality? And this is a field. This is a field which exists in string theory. It's called the Kalb-Ramond field. Not important what it's called. It is another field which appears in string theory.
Which one is the singlet? Which one is the triplet? Which is the singlet and which is the triplet?
Oh, no, wait a minute. Both of these are polarized like photons. There's one more nobody asked me about. What about A55? A5, A5. Left, right. That one's the one that behaves like the scalar. That's the one associated whose field quanta, these are the field quanta of this one over here. Okay? Namely the radius of the compact direction. So they're all here.
Which one corresponded to a winding number, the other corresponded?
The one with the plus sign corresponds to momentum, and that's the one that's associated with gravitons. The one with the minus sign is associated with the winding number. Yeah. Okay, so now we have a more complete idea about T-duality. It involves momentum being interchanged with winding number. It involves R being interchanged with 1 over R. It involves replacing dx by d sigma with dx by d tau. This is the integral of this is winding number, the integral of this is momentum. And finally, it involves interchanging g mu 5 with b mu 5. All right, so these theories have more, now of course, not clear that the ordinary world does have such fields. We don't know of real particle candidates for all these fields. We don't. Okay. So this is, at the moment, a mathematical construction, and we're exploring a mathematical construction. There's lots of ideas about how to use these constructions. But at the moment, I think we should regard this as an exploration of the mathematics of the theory. There's plenty of room in physics for these objects, incidentally. But I don't want to get into the phenomenology of them. Good, so there we are. That's what T-duality is. After 5 minutes, we're going to come back and talk about T-duality for open strings and how it leads to a new concept, completely new concept called D-branes. So let's take a break. Yeah. Okay, so we've figured out what T-duality is, this very strange interchange of big compact geometries with small ones and various other things going on. I want to concentrate now on the aspect of T-duality that has to do with, well, let's erase some blackboard here. This one. Now you're going to see the kind of gymnastics that the kind of deductions that people have made over the years. This T-duality is one of them. They're implicit in the mathematics. Many of them are very surprising. We're going to talk about D-branes and how one was forced to have these new objects in the theory, which are called D-branes. D stands for Dirichlet. Dirichlet had nothing to do with them. He was dead for many hundreds of years. They should be called P-branes for Polchinski, but P-brane was already a term in use. Brane is spelled B-R-A-N-E, like membrane. And one speaks of D-n-branes. D stands for Dirichlet, not for the dimension of space. N stands for the dimensionality of the brane. A string is a one-brane. A membrane is a two-brane. A solid three-dimensional chunk, which may be embedded in higher dimensions, but solid three is a three-brane, and so forth. So there's DN brane. Where do they come from? What do they do? What's their, they're not just made up things. They were essential to the consistency of the theory. The mathematics absolutely demanded them. And the result of knowing about them has been to derive an enormous number of equivalences between different theories. And in fact, it turned out that those enormous numbers of equivalences turned out to be enormous numbers of equivalences between different kinds of geometric structures. Equivalences which the mathematicians had no idea existed. Equivalences between different Calabi-Yau manifolds, and which the mathematicians were entirely surprised by, and they turned out to be able to confirm them. But this is now part of the gymnastics of string theory, and D-branes have played an enormously powerful role, also in the applications of it. So let's talk about open strings now. D-branes have to do with open strings. Open strings, what's the winding number of an open string? Open strings don't have stable winding numbers. If you have an open string on a compact space, now this picture is sort of shorthand for all of the compact directions, of which there are presumably 6 in superstring theory, and all of the open uncompact directions. All right, but let's imagine now that in addition to closed strings, there are open strings. Open strings now have endpoints. We can't classify them with winding number. It doesn't make sense to classify them with winding number. They're not wound. So we have to think about what happens to them when we do this process of T-duality. T-duality was a phenomena discovered in closed string theory, but surprisingly, it also makes sense for open string theory, and I'm going to show you what it says. It says something rather remarkable, something which is confirmed in other ways, but this is the simple way to think about it. There's a string, an open string, and what are the rules for open strings? Do you remember what the rules are for what goes on at the end of an open string? The boundary conditions on the end of an open string? Neumann. The end of an open string should satisfy dx or dy. Again, this is y, this is x, any of the coordinates, but let's in particular, well, let's write them both. dx by d sigma equals 0, dy by d sigma equals 0. And what does that correspond to? That corresponds to the idea that the end of the string, here's a string, it's made up of a lot of tiny infinitesimal mass points, and supposing the end of the string had some net stretching, the x by d sigma was not equal to 0, that would exert a force on the very last molecule. Well, as you subdivide the molecules into smaller and smaller structures to go to the continuous limit of the string, the molecules get lighter and lighter and lighter. How much force can you put on a thing of arbitrarily small mass without having it accelerate with an infinite acceleration? The answer is 0 in the limit. That means that the string cannot afford to have any net stretching at the end of the string. So that's where these conditions come from. The x by d sigma, dy by d sigma should be equal to 0, and that's to forbid infinite accelerations either in the x direction or the y direction. Of course, there is another possibility, and that's that somebody's holding the end of the string and applying an enormous force to keep it from moving. But if nobody is standing there holding the end of the string, then if there's any net tension in the end of the string, it will accelerate infinitely to basically to remove that stretching. Okay, now, what about T-duality? Let's suppose now that this was a small compact direction, and we want to replace the theory. It's very, very much smaller, extremely small. And we want to say, wait a minute, this is supposed to be equivalent to a theory with a large compact direction. Here's the large compact direction. Enormously large, could be cosmologically large. What do I do with these open strings? Okay. Well, we're supposed to replace winding number by momentum, but remember that momentum was, what was momentum related to? It was related to dx by d tau, right? Velocity. What was winding number related to? Dx by d sigma. Namely, exactly what goes on here. Okay. I should actually write, since I'm mostly interested in the compact directions for the moment, let's concentrate on the compact direction. T-duality involves, among other things, replacing, every place you see it, dy by d tau by dx, or dy by d sigma by dy by d tau. Okay. So, what does it say then about open strings? Open strings, when you replace, when they undergo this process of T-duality, what you have to do is you have to change the boundary conditions. And the boundary conditions at the end of the string become the x by d tau equals 0. Or in this case, the T-duality is associated with the compact directions. We don't want to do that. Only the compact directions are being interchanged small with large. We're not diddling at all with the uncompact direction. One compact direction, y goes, the radius in the y direction becomes big. All right? The rule was we were supposed to replace dy by d sigma by dy by d tau. If strings originally moving on the surface had Neumann boundary conditions, that's dy by d sigma equals 0, after T-duality, they have Dirichlet boundary conditions. What does it mean to say that dy by d tau is equal to 0? Oh, incidentally, this is only at the endpoints. This is at the ends of the string. It means the endpoints are forbidden from moving. So wherever they started, they are stuck at. Where are they stuck? Well, wherever they're stuck, there's something holding them there. It means that this theory has objects in it which can nail down the ends of strings. There are strings, there must be, if T-duality is to make sense, there must be objects in the theory which can nail down the ends of strings. You start with a theory with no such object, and the strings just move freely, and after T-duality, you discover there's some kind of object in the theory which has nailed down the location of the string. It's nailed down only the y component. We have not played around with the x's. The x's are still free to move. The compact direction here is now nailed down. So where is it nailed down? Here's a space. It's nailed down someplace. Someplace in y. Y goes around this way. Let's put that place right over here. There's something here which is capable of holding the ends of strings, nailing them down. That object is called a D-brane. D for Dirichlet. And it wasn't put in by hand. Instead, one asked, what if there are open strings in a theory and the theory has T-duality, which it must have for reasons that are by now well understood? Then what happens to the open strings when you interchange the small compact direction for the large compact direction? And the answer is that you discover something new. You discover some new kind of object which is holding down those strings.
Excuse me.
Yeah.
Is it necessary that the y value be the same for the ends?
No, I think you're asking whether this can bend. I drew it so that it. Oh yeah, it could. That's right. But the simplest case is where it's just fixed in some position. Now, what position do you put it at? Here, here, here? Well, the answer is that you better be able to put it anywheres. So, therefore, this has to be a movable object because there was nothing special about one point in space and the other point in space along these axes. So, there's got to be a movable object which functions as an anchor point for the ends of strings. If it's movable, then you can be quite sure that it's also bendable. Relativity can't make sense with absolutely rigid objects, and so it will also be bendable, but let's just not bend it for the moment. And strings can attach themselves to it, or strings attached to it can exist. A string can come, good, these are called D-branes, right? This is first of all, supposing we took, let's take an example. Supposing we took 10-dimensional string theory, which has 9 dimensions of space, 9 dimensions of space, and we made one of them compact, and then introduced a D-brane in this way. What would be the dimensionality of the D-brane? Would it be 1? 9. No. 8. 8. We've pinned down one direction and left the other 8 directions of space free to move around. All right, here's a tabletop. That tabletop is 2-dimensional. If there's an object attached to the tabletop, how many directions is it free to move in and how many is it constrained in? It's free to move in 2 directions. Here's a string. Here's a string with 2 ends, or my finger is the end of a string. It's free to move in 2 directions and constrained in its 3rd direction. All right? So if I constrain one dimension, it creates for me in 3-dimensional space a 2-dimensional surface. Supposing I'm now in 9 dimensions of space, and I constrain the end of a string, I constrain one of the dimensions. It becomes an 8-dimensional surface that the string can move around. Now, suppose there was no reason for only constraining. You can do the same thing with any number of compact directions. You can play this T-duality game with any subset of the compact directions. You can play that, it's the same game, and you can, in the same way, construct D-branes which pin down any number of the coordinates that the end of a string can move in. All right, so let's take 3-dimensional space again. Let's suppose now we've played this game and we've constrained the vertical position by doing this T-duality trick with respect to the vertical direction. Supposing I also do it now with respect to the front to back direction. I constrain the motion of the position of the end of a string so it's constrained vertically and this way. That means that the end of the string has to move along the intersection of this plane with that plane. So if I constrain 2 dimensions, what kind of brane am I talking about? A D, in this case D1, but if I started with 9 dimensions of space, 7. So each constraint removes a direction that it's free to move in. All right. For that reason, you can have in 9 dimensions, by playing this game over and over again with the different directions associated with a compact space, you can have D8 branes, D7 branes, D6 branes, all the ways down to what's the maximum number that you can you can just get rid of the freedom to move in any of the directions of space. Then what would you call the brane? D0. D0. It's a point. It's a point in space that the string is connected to, and it's not free to move along any of the directions. That's a D0 brane. Zero dimension means a point. You're going to have from D0 branes to D8 branes. They all make sense. And their existence, in some sense, is all necessary to the consistency of the theory. D0 branes are a new kind of particle, an unexpected new kind of particle. Yeah.
You said you weren't removing them from non-compact directions, so wouldn't you really start subtracting from 6?
Yes. No. Well, not really. No. No. You could, no, I'll show you why in a moment. Right. Okay. We've played this game with the compact directions. But now let's imagine, having done this operation, let's imagine shrinking and shrinking and shrinking this until it becomes arbitrarily small. What happens on this side? It gets bigger and bigger and bigger. Okay? So eventually, on this side, it can be so big that it's completely mistaken for a non-compact dimension. In other words, if a dimension of space is big enough, for all practical purposes it becomes non-compact. What we've demonstrated by this series of arguments is that even in the non-compact directions, there must be objects which are the anchors of strings. They can be oriented along compact directions, they can be oriented along non-compact directions, any number of them. And of any dimensionality starting with 0 and going up to 8 dimensions. Actually, you can go up to 9 dimensions, but that means they completely fill space, and that simply means that we're talking about open string theory in which the open strings are just free to move, but they're not, we wouldn't call them branes. There are things that people call D-1 branes, but you don't want to know. They're not real concepts. Okay, so you start, here's a D0 brane, it's a point in space, and a string end can end on it. Where's the other end of the string? It could be on another D0 brane. Or it could be stretched out to infinity. That's not a good thing because it becomes infinitely massive. Or it could even come back to the same point. The same D brane. That's a D0 brane. What's the next one up? A D1 brane. A D1 brane, something very interesting about a D1 brane, it's a line. Now, as you already pointed out, it does not have to be a straight line. We deduce their existence in this way, but once we know that they exist, and once we know we're talking about a relativistic theory, they have to be bendable. If they're bendable, they can even bend around on themselves. They're structures which are physical objects, and they have strings connected to them. But now let's forget the strings that are connected to them, and the strings connected to them could be like this. Let's forget the strings that are connected to them and just look at them. This is a one-dimensional object. It's called a D1 brane. It's a one-dimensional object. It can bend. What's another name? In fact, it can not only bend, but it can even come back on itself. What's another name for one-dimensional objects like this? Strings. But are they the original strings? No. They are not the original strings. They're called D1 branes, and they're distinct from the original strings. How would you expect they might be distinct from the original strings?
They're not the same all the way around. You got points on them that have particles and points that don't. I mean, you have strings that are attached someplace and are not attached.
Well, they may or may not have strings attached to them, But let's for a moment suppose they don't have strings attached to them. They're much heavier. In string, and that makes a lot of sense because how did they start out? They started out as anchors, like infinitely heavy things that could hold the strings down. But they're not really infinitely heavy. Their mass depends on some coupling constants and so forth, depends on various things. They're heavy. They're much, much heavier than the ordinary strings. And so in that sense, they're anchors. But they are string-like.
Does the T-duality hold for them as well?
What's that?
Does the T-duality hold for the brains that don't like strings?
Yeah, it also it holds for the brains too. Yeah, it does hold for the brains. What's the next one up? A D2 brain. A D2 brain is called a membrane. Membranes, D2 brains, and those are simply sheets, like the tabletop here, that string ends can move around on, or pairs of strings can move around on them like that. These are D2 brains. Next one up, D3 brains. In a three-dimensional world, a D3 brain fills space. All right, so it fills space. It's a space-filling brain, people. And in other words, it's just space. And if we had a D3 brain, then that would simply mean that we can have open strings that can just move around. They have to be attached to the brain, but the brain is everywhere. And so it's just open strings that are free to move around everywhere. So it's often said that ordinary open string theory is string theory on a space-filling brain. But if we're living in a world with higher dimensions, then a 3 brain doesn't fill all of space. It's like a 2 brain in the 3-dimensional space. It's a surface, and strings can move on it. Okay, that's the idea of D-brains. And as I said, and as I emphasized, they are mathematically important to string theory, but they also are the origin of a lot of applications of string theory. So let me very quickly tell you what's known. You can start with one of these D-brains. Yeah.
I assume that the unconstrained directions that are left over can be compact directions as well.
Yes, 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 that's correct. That's certainly correct. Right. Okay, let's imagine a D-brain. And I'm going to draw it as a D2 brain. There's the D2 brain. Now, if you say to yourself, well, this is awfully slick, do I really believe that this has to be? Not from the arguments that I've made, obviously. I'm giving you some sketches of arguments. Whether string theory is the right theory of nature is not the issue here. The mathematics of this is very, very tight by now. I mean, many, many cross-checks, many, many different things point in the same direction. The mathematical theorems that have come out of it, or the mathematical speculations have been confirmed in mathematics. So it's remarkable and presumably correct. All right, here's an empty D-brain. Right. Think of it as empty. Empty means it has no strings ending on it. Think of it as empty, and think of it as an empty space-time, or an empty space. The space now is not the full space, but it's just a surface in space. But think of it as a space. It's empty. We can put things into it. We can put strings into it, like this. Little open strings. And these open strings are free to move around. Now I'll tell you what the basic process of them is. The basic thing they can do is their endpoints, these are oriented strings, so they have arrows associated with them. When the endpoints come together in string theory, let's say the endpoints come together, if we have two endpoints, one with an arrow coming into it and the other with an arrow coming out of it, it can do the obvious thing. Namely, the endpoints come together and lift off the surface and form a single string with two endpoints like that. How do we think about that? If these strings like this are thought of as particles which are free to move around, and in string theory, particles are strings. These are very much like the original open strings that we started with. If we think of them as particles which are constrained to move on the surface or very close to the surface, then what we discover is that these particles can split and join. Two of them can come in, join into one. One of them can go out, separate into two. We're starting to build up something that looks like particle processes. We're starting to build up something that looks very much like Feynman diagrams. Two of them come in, join to form one. Maybe it hangs around there for a while, and then the reverse process happens and it becomes two again. We're building up the kind of processes that quantum field theory describes: creation and annihilation of particles, transmutation of the number of particles. And so it's not completely surprising that the mathematics of the interactions between these particles looks very much like quantum field theory. In fact, at low energies where you don't have enough energy to really excite the vibrations of the strings, it is simply quantum field theory, where the particles of the quantum field theory are these open strings. In fact, the open strings behave like photons moving around on the surface. They're not photons in the sense of the 10-dimensional theory. They're photons in the sense of a theory which lives and whose particles live only on the surface. That's the basic connection between brains and their application in studying quantum field theory. Brains like this define quantum field theories, and they define quantum field theories in exactly the way that I've just described. But, yeah. Let's, incidentally, these open strings connected to the brain here do behave like photons moving around in the brain. They behave like photons in the lower dimensional theory. But let's imagine now that we had more than one brain. There's no reason why you can't have several brains, for example, parallel to each other. Here's two brains parallel to each other. You can move them closer and closer until they touch, in which case they just form a compound brain, or you can leave them separated. Let's leave them separated for a moment. Let's put three of them in just for fun. Three parallel brains like that. And let's think of the kind of excitations that can move around on them. Well, you can have, and the excitations means ordinary strings. An ordinary string, let's give them names. Let's give the three of these names. And the names I'm going to give them are red, green, and what, yellow? Blue, sorry, blue. Blue. Red, green, and blue. This is just the names of the three brains. Of course, we could have 4, or we could have 7, or we could have 15, but I'm particularly interested in having 3 of them for the moment. What kind of strings do we have? We can have strings which begin on red and end on red. Oh, remember, these strings are also oriented. Keep in mind that they're oriented, and so what would you call this string? I would call it a red anti-red, or a red-red string. This is a red-red string, and therefore some kind of red-red particle. We can also have red-green particles. Red-green particles are ones which look like this, where one end begins on red, the other end, and the other ends on green. So what do we have? What are the class of particles we have? We have particles that are labeled by 2 indices, 2 colors. For the case of 3 brains, we have 3 distinct colors, and we have particles which are labeled by pairs of colors. One associated with the outgoing and the other associated with the incoming. Does this sound like anything you've seen before? Gluons. Gluons in quantum chromodynamics.
How do you go from red to blue?
What's that?
Can you go from red to blue?
Yeah, go ahead.
Of course. Sure. Okay,
No
so
problem. Maybe you should keep in mind that this is embedded in a higher dimensional space. So to mimic that, let's think of lines in higher dimensional space. Now there's no problem in going from here to here or from here around to here. You're worried about passing through here.
Well, I'm worried if you have to merge a red-green with a green-blue to get a red-blue.
Well, there will be some rules. There will be some rules. And the basic rule, what is it? The basic rule is really only one rule, but we can use it over and over again. A red-green string, what can it do if it hits a red-red string? All right, let's suppose this is going out here and coming in here. Let's suppose this is going, let's see what I want to have. I want to have in here and out here. Okay, what can happen? This end can join with this end. They can come together and join and form a single string which goes all the ways from here to here. In other words, the red anti-red, the thing coming into red and the thing going out of red, one in, one out, can join and simply make a single string. This is very much like a green-red gluon coming together with a red-red gluon and forming another red-green gluon. Same rules, exactly the same rules as for gluons, but the string cannot annihilate or lift itself off the surface. On the other hand, if we had this situation here, then these can come together and they can lift themselves off the surface. That's incidentally why there are 8 gluons instead of 9, because one linear combination can disappear and is not stable. So the mathematical rules for splitting and joining are exactly the Yang-Mills quantum chromodynamics rules for gluons. Okay, what about quarks? Okay, so now what about quarks? What is a quark in this language? A quark in this language only has one color. It's either a quark or an anti-quark. It only has one color. It doesn't have 3 colors. Sorry, it doesn't have a color and an anti-color. A quark must be a thing which only has one end. A quark in this language is a string which ends on one of these branes and goes off to infinity. Okay? Now, it doesn't really have to go off to infinity. It could go off to some distant brane of a different kind, but it doesn't have another end which ends on one of these 3. That's a quark, and it's either a string coming in or a string going out. When a string coming in and a string going out meet each other, they can join and just disappear out into off the brane. They can join and disappear from the brane. That's annihilation of a quark and an anti-quark. If there's 2 quarks, they can't annihilate. They're stuck there. And that's exactly the same rule as quarks. The mathematical structure of the field theory that described these strings moving around is essentially, with some little extra added ingredients because of supersymmetry, it's a supersymmetric version of quantum chromodynamics. And it is part of the reason that branes are interesting for exploring quantum chromodynamics. I'm not going to show you how they're used in detail. I'm just showing you what the connection between things is. Let's suppose there's only one brain. Then it's not like quantum chromodynamics. What do you think it might be like? Now we have objects. We don't have to name them red, red, green, blue. It's just a string. It's like quantum electrodynamics. It has only photons. It doesn't have this complicated gluon structure. These would be photons, and what would these things be? Charge. Electrons. They could be coming in, or they could be going out, in which case they would be electrons and positrons. When two of them come together, they can annihilate. One last point, which is really quite fascinating. Remember I told you that there are ordinary strings and D strings. D strings were these new objects that we discovered. These new objects which are a good deal heavier, but they're also strings. An interesting question is, can a D string also end on a brain like this? Incidentally, I'm thinking about three brains because I'm thinking about mimicking three-dimensional space, D3 brains. So these are really D3 brains. Interesting question, can a D string is itself something that ordinary strings can end on, but let's forget that. Can a D string end on a 3 brain, a D3 brain? The answer is yes. I'm not going to try to prove that for you. That's a much more elaborate question. But then, if ordinary strings, the ones we started with, make electrically charged particles, what do D strings make at their ends when they intersect the 3 brain here? Can you guess? Neutral? Nope. Well, they're in some sense neutral, but they got to be something which is similar to what happens when ordinary strings end. Magnetic monopoles. Remarkable. The magnetic monopoles are much heavier than the electrons because these strings are much heavier. Magnetic monopoles are expected to be much heavier than electrons. They become magnetic monopoles. The relation between magnetic monopoles and electrical monopoles in quantum electrodynamics is mimicked by the relation between D strings ending on these things and ordinary strings on them. So I've told you a lot of stuff. I don't expect that you're going to follow every detail, but I'm trying to show you how string theorists discovered. It took a long time to make. I mean, this didn't happen all in one day. This happened over a period of 20 years, basically, or more. No, more than 20 years, 25, almost 30 years, that all these pieces were put together by various people, a very wide variety of people who saw these connections. And today, string theory and its description in terms of brains is the primary tool for studying quantum chromodynamics. It's very bizarre. The whole thing made a full circle. It made a full circle from a theory of hadrons to a theory of quantum gravity to the presence of D brains that was necessarily there, which when you put them together in the 10-dimensional space, put together 3-dimensional D brains, all of a sudden becomes the theory of quantum chromodynamics that it started out as. So that's, I don't know what to describe it. I describe it as sort of mental gymnastics, but I think it's more than that. I think it's a process of discovery and unraveling of the mathematical structure of this thing. It has wide application to quantum chromodynamics, other quantum field theories, fluid dynamics, all kinds of things. So far, it has not had application to a direct application to understanding the particle spectrum. And that's probably because it's just too complicated. Yeah.
What determines which of the dimensions the T-duality is applied to?
Oh, you can do it to any dimension you please. To any compact dimension you please. You choose one that's convenient, but that eventually just winds up saying that these D-branes can lie along any axis, and what chooses it? The history of the universe.
Is the membrane for magnetic monopoles, magnetic monopoles D3 and for
No,
quarks?
the universe here, from our point of view, is a 3-brane here, D3 brane. But if from some of the other 10 dimensions, which the people who live on this world don't even know about, but a string ends over here and happens to be a D string, they'll experience that as a magnetic monopole.
So that means these D strings are oriented as well.
What's that?
They must be oriented as well then?
The D strings are also oriented, absolutely. Yeah, they're also oriented.
You use two planes for SU2,
Yeah.
and how do you get the feature where it's not reflective? In other words, SU2, if you have a reflective universe, the physics doesn't work the same way.
Parity.
Oh, you're talking about charge conjugation violation. You're saying
I don't know the term, but I'm talking about how we had left-handed and right-handed.
or particle and antiparticle. More interesting, yeah. There are answers. String theory certainly has a potential possibility to describe that, but not at this level. At this level, you need, when you have Calabi-Yau manifolds, they can have more complicated asymmetries that allow that. This toroidal compactification doesn't allow it. There are many, many other objects in the theory which I haven't gotten into. These are the simplest to describe. There are lots of other constructions and other kinds of objects that the theory has to have. And some of them, when they intersect other ones, break various symmetries, and we can talk. We can discuss them some other time. I'm out of time, I'm out of energy, and I'm out of momentum, and
For more, please visit us at stanford.edu.